world is falling apart. Bridges collapse. Pipelines explode. Buildings decay. It's an all-out war on rust and rot.
This is a massive generational undertaking that will cost billions of dollars over several decades.
The Navy has taken the battle indoors, while robots take on pipeline intruders. And automakers dream up new torture tests for vehicles.
It takes roughly 20 weeks to simulate 10 years of corrosion.
But mountains of decaying garbage produce energy.
This is like the epicenter of world bioreactor research.
And the termite that attacks 600,000 homes each year may lead to an energy promised land. Now, corrosion and decomposition on Modern Marvels. Chronicle the failing infrastructure in the United States. Every 4 years, the American Society of Civil Engineers issues a report card.
The report card on America's infrastructure breaks the country's infrastructure into 15 categories, ranging from bridges, airports, water, wastewater, sewers, and gives each of them a grade, similar to what someone would get in a report card in school from A to F. ASE has given the nation's infrastructure an overall grade of D.
The primary cause for our failing infrastructure, corrosion.
All of the categories that were rated by ASE for the infrastructure are affected by corrosion. It's lack of maintenance that shortens the life of infrastructure.
Corrosion costs the U.S. economy $300 billion each year. That's 4% of our gross domestic product, nearly half of what we spend on foreign oil, or roughly $1,000 per American citizen annually. Corrosion's destructive power can be found everywhere, from rusting railroad trestles to deteriorating oil pipelines. But what exactly causes this scourge that eats away at our society?
Many different environments can cause corrosion. A corrosive environment can be seawater, can be the atmosphere, can be a chemical solution, an acid.
It's a natural electrochemical reaction occurring on an atomic level in most metals. Water conducts electricity that allows the exchange of electrons on the surface of the metal. Positively charged atomic particles called ions flow from the metal and combine with the oxygen in the water to form an oxide. In the case of iron, that oxide is rust. Iron is found as an ore, iron oxide. We put energy into the ore to produce pure iron. When this iron is exposed to a corrosive environment, it rusts, releasing that stored energy and reverting to an oxide state. Different metals corrode at different rates. Reactive metals like iron oxidize very easily, while more passive metals like gold resist corrosion, earning them the title noble metals. That's why you'll find non-oxidizing metals such as platinum used in medical implants. But in a world with an infrastructure built primarily of iron and steel, corrosion is rampant, and its impact can be catastrophic.
The I-35W collapse was a wake-up call for a lot of the nation in terms of infrastructure. Infrastructure has a definite lifespan. Corrosion can shorten the life of a bridge, can shorten the life of a concrete deck. Right now, if you look at the country, we have roughly 12% of the bridges structurally deficient and 12% of the bridges functionally obsolete.
The Bourne Bridge in Massachusetts is listed by the Federal Highway Administration as one of the 20 most structurally deficient in the nation. It's joined by the San Francisco-Oakland Bay Bridge, which serves 250,000 vehicles each day. The Department of Transportation also gives a poor rating to this aging American landmark. Just repairing the corroding approach ramps on the Brooklyn Bridge will cost $275 million.
It was estimated in 2005 that it would cost $9.4 billion a year for the next 20 years to remove all of the deficiencies of our bridges.
America's bridges may be bad, but our transit system is worse. It's estimated that our corroding urban rail system requires $14.8 billion annually just to maintain existing poor conditions.
Right now, a lot of the departments of transportation are having to make a choice when it comes to either building new structures or maintaining the existing structures.
Maintaining Mass Transit's corrosion-prone steel support structures requires special protective coatings. Zinc primers and urethane top coatings combine to preserve the steel for extended periods. But even coatings can't stop corrosion caused by what many transit authorities consider their worst enemy, stray current. It's a phenomenon commonly found in modern subway systems powered by direct current. In New York subway, the direct current is delivered via the third rail.
There are 600 volts of direct current at almost unlimited amperage going through the third rail. If you touch it, you'll instantly be killed.
The third rail provides direct current power to the subway train, then loops back through the system via the running rails, returning to the substation, completing a cycle. Current from the rails tends to stray into the soil, attracted to any metal object that might be buried nearby. Corrosion dramatically accelerates at the point where current leaves the buried metal object. Older transit systems are most susceptible to stray current corrosion due to general deterioration and poor insulation. New York City's 100-year-old Mass Transit Authority ranks corrosion as its #1 maintenance issue. But according to the American Society of Civil Engineers, we have far bigger corrosion problems to worry about.
The worst areas with a grade of D- are drinking water, wastewater. The Environmental Protection Agency estimates that nearly $1 trillion is needed in critical drinking water and wastewater investments over the next 20 years.
The very nature of wastewater is corrosive. It breaks down, and that increases the acid content in wastewater. What that means is it essentially eats away at the pipe, weakening it. It becomes much more subject to leaks and structural breakdown, which is sewer pipe collapsing.
Collapsed sewer pipes mean spills, and spills mean fines from the Environmental Protection Agency. Detroit, Atlanta, and Washington, D.C. have seen their fair share. But the worst offender is San Diego, with $6.2 million in EPA penalties between 2005 and 2008.
Some of these structures are from the early part of the last century, and they're wearing out.
Here in the city of St. Louis, we have the 4th largest sewer system in the United States, parts of which date back to the 1850s, before even when Abraham Lincoln was president. We have wooden sewers, actually, downtown, and those wooden sewers are amongst the first sewers that were built in the 1850s. But it's the infrastructure that we have today.
The $1 trillion price tag on our aging water and sewer systems may be reduced by invented new technologies, like those used to overhaul St. Louis's 10,000 miles of underground pipe. To save time and money, the city is rebuilding its sewers from the inside out.
The conventional way would be to come out here with a backhoe and dig up the street and put in a new pipe, but that's very expensive, very time-consuming. In lieu of that, we have cured-in-place pipe. What that is we're working with polyester resin. That's the same thing that boats are made out of. What we're essentially doing is we're using the old pipe as a form, and we're building a new pipe inside that without digging up the street. We're going to have this done in one day.
Trenchless repair systems, developed by in-situ-form technologies, are rapidly overtaking traditional dig and replace methods of pipe restoration. It starts with an inspection by an iBot that doesn't mind crawling through sewers.
That allows us to get a video of the pipeline before and after we install a liner. It works basically on its own power. You run this through the line initially to make sure it's clean, so when we drag our liner through, there's not going to be any bumps or anything that's real ugly in there. It feeds basically into our TV truck, and I can see everything on a television monitor without actually having to go into the line.
The robots aren't afraid of tight places or unexpected visitors.
every now and again you get to see some crazy stuff.
In trenchless technology, instead of unearthing the corroded pipe, a resin-saturated coated felt tubing is inserted into it. Compressed air inflates the tube, extending it the length of the pipe. Installers then circulate steam through the tubing, curing the resin and forming a tight-fitting pipe within the pipe.
What this is, it's thermal set, heat set. So when we raise the temperature, in this case to 130 degrees Fahrenheit, it's going to exotherm. In other words, it's going to go from liquid to solid. It's a chemical reaction. It's kind of like when people buy an epoxy at the store and you got two parts and you mix them together. There's heat generated there, and that goes from liquid to solid. The pipe's going to be solid, just like this pipe in my hand. This is an 8-inch. Here's the felt. This has the resin in it, installed in the pipe. And then when we finish, it'll be a structural pipe.
The crew relies on the eyebot to finish the job by attaching a movable drill to the front of the eyebot. A technician can reopen access to individual homes, called service laterals, that have been sealed by the liner within the pipe.
Basically what I do is when I approach a service, I find the dimple where the service is at. So this is what we're looking for. That's how I know what I got to cut out. I get my bit up to the service and I will cut a hole in the middle of it. Generally it takes about 5 minutes to cut a service. We can line an entire street and reinstate everybody's laterals to their houses and have their water flowing in one day.
What this will allow us to do is restore this line, maintain service to these customers without tearing up several blocks of street and causing a major inconvenience for everybody that lives in this neighborhood.
Trenchless sewer replacement costs up to 50% less than traditional methods. It works equally well with drinking water pipes. But not every city is as proactive as St. Louis in restoring their corroding sewer and water delivery systems.
Many communities are faced with a countdown of sorts as to which of their infrastructure is going to fail most rapidly and maybe even most dramatically. And while this underground assets tend to not be as spectacular as a bridge failing or a road failing or even a large sinkhole, but they can contribute mightily to environmental degradation with sewer leaks and even quality of living issues.
If the mix of metal and water in America's infrastructure is a recipe for corrosion, what happens when you add salt to the equation? For the U.S. Navy, it's a recipe for disaster, unless you've got the most advanced research in the world on your side. According to 2007 U.S. Bureau of Transportation statistics, 53% of Rhode Island's bridges are structurally deficient or functionally obsolete, the highest rate in the nation. Corrosion and decomposition will return on Modern Marvels. The United States commands the largest navy in the world. More than 280 ships and 3,700 aircraft currently patrol seas from the Far East to the Mediterranean. But if you're looking for the largest fleet in the Pacific Ocean, you'll need to go 30 miles northeast of San Francisco to the backwater port of Suisun Bay. Most of these vessels are past their prime, mothballed rust buckets that will never see action again. Over 70 derelict ships moor in the bay. Cargo ships, missile cruisers, and tankers, most between 400 and 700 feet in length. These relics date from as far back as the 1940s and include among their ranks the distinguished battleship USS Iowa, launched in 1943. Officially, the Navy considers them reserve ships. Unofficially, they're known as the Ghost Fleet. The only battle these veteran warriors fight today is one against corrosion.
We have to deal with the water and the salt in the water coming up and corroding inside of the hull. You don't want holes in the hull of the ship. You don't want to take water on the vessel.
As they await disposal, the rusting hulks have shed over 20 tons of toxic metals into the bay, including chromium, lead, and mercury. But corrosion isn't just a problem for the aging Ghost Fleet. It's a costly burden for the entire U.S. military.
The cost of corrosion, Department of Defense-wide, has been estimated to be somewhere between $10 and $20 billion per year.
That's roughly the equivalent of what Canada spends annually on its entire defense program.
Of that, the Navy's cost of corrosion for ships and submarines alone, not including aviation, is about $2.4 billion every year. That represents on the order of 20 to 25% of our maintenance costs yearly, as well as sailors spend a lot of time performing corrosion prevention.
It's a never-ending task of having the crew trying to fight this corrosion and scaling and chipping and painting and repainting. And it seems like you just painted there and now you have to paint again, but that's just what you have to do to keep the ship from rusting away.
The culprit that accelerates corrosion aboard ship is salt water.
Salt water is more corrosive than fresh water, and it acts as a conduit for the electrons to flow from one area of the ship to the other. And the areas of the ship that the electrons are leaving the iron creates rust areas.
Shielding a ship's metal surface with sealants and paint is the first line of defense against salt water. The Navy also uses another extremely efficient means of combating corrosion. Credit Englishman Sir Humphrey Davy for that method. He attached a chunk of iron to the hull of a copper-clad British naval ship. It's called cathodic protection, and he introduced it in 1824. The iron, with its greater tendency to oxidize, reduced corrosion in the copper. Cathodic protection works because water and the ship's metal hull in contact with the water act like a battery. The salt water is a conductor of electric current. The ship's hull becomes a cathode, with current flowing in. The corrosive or sacrificial metal becomes an anode, releasing current. The flow of current from the anode to the cathode releases ions from the anode, causing it to corrode instead of the ship's hull. This is a 20-pound zinc anode, used on the submerged hulls of ships. This is a similar piece of zinc after 1 year as a sacrificial anode. Today, the Navy uses an even more effective form of cathodic protection, called impressed current.
This is our cathodic protection device. It applies a voltage to the hull of the vessel. It's helping to protect the hull of the ship from corrosion. It has 6 anodes underneath the waterline that 0.85 volts is applied to. What the system is doing is it's putting a charge on the entire hull, so the entire hull has an equal potential throughout.
The 0.85 voltage is so low that it's undetectable to the touch, but still enough to prevent electrons from leaving one area of the hull and traveling to another, causing corrosion. Still, you can only slow corrosion. You can't stop it.
The elements in the environment are always trying to take the ship back to nature, and it's our job to try and keep nature from doing that.
In its endless war against corrosion, the U.S. Navy comes here.
This is the Naval Research Laboratory's Marine Corrosion Facility. We're on the Naval Air Station in Key West, Florida. This is where we will test run many of our new technologies and new systems for corrosion mitigation in the marine environment.
The lab's cathodic protection design facility is at the cutting edge of corrosion research.
The tank that we're looking at here is a 30-foot diameter tank that's 10 feet deep and holds about 55,000 gallons of water. We are looking at a scale model of the Zumwalt-class destroyer. This is the Navy's new destroyer, and this is a fiberglass replica of the hull that's been laid out for cathodic protection design.
The fiberglass hull is studded with steel chips to replicate paint damage. The water in the tank is agitated to simulate a ship's motion.
The model gives us a very cost-effective method of doing this. We don't have to work with the real ship, and we can change component locations in real time.
The model is scanned to determine the best placement of cathodic protection on the hull, information that will be used in the construction of the actual ship.
This is the only facility of its kind in the world. We designed for both the U.S. Navy and have done work for some commercial sector and also other navies of the world.
Also one of a kind is the facility's full-scale ballast simulation tank, where researchers can study new preservation methods.
Ballast tanks are our #1 corrosion issue in the Navy, mainly because we store seawater in them. We store seawater in ballast tanks to adjust ship trim and list as well as buoyancy. Because of the fact that there's such a large corrosion problem, we invest the majority of our R&D resources into new coating systems, monitoring technologies, and inspection methods.
One of those monitoring systems is a robotic camera that inspects and quantifies ballast tank corrosion.
We use it to actually take still imagery of the tank and actually analyze the percent damage to the coating within the tank. It's a useful device because it allows us to remotely assess the state of preservation without having to enter the tank, gas-free the tank, which is important for safety and cost reasons.
To reduce time spent painting ballast tanks, the lab experiments with long-lasting, fast-curing coatings.
Here we have a rapid cure technology that consists of a base component and a catalyst component. When I mix these two components together, essentially what's going to occur is an exothermic reaction. As the exothermic reaction progresses, the process generates a great deal of heat. It's going to get as hot as 275 degrees Fahrenheit. Now what has occurred here is we've made a liquid to a solid in less than 2 seconds as the reaction took place.
With rapid cure coatings, time spent painting a ballast tank can be reduced from 200 to less than 40 hours. The time sailors spend in corrosion prevention also has a surprising hidden cost.
We recruit sailors to drive highly sophisticated war machines. When they get to the deck plate, they find out that they're spending quite a bit of time doing corrosion prevention. The fact that these sailors are spending so much time chipping and painting has actually impacted our retention rates.
This experimental heat induction tool might be just the thing to keep sailors from jumping ship.
This is a tool that generates an electromagnetic field and causes the substrate to heat up, resulting in the coating actually popping off or losing adhesion from the surface. So it's very easy to just chip the paint right off.
Reducing maintenance time is critical for today's Navy.
As our fleet has gotten smaller over the years, the operational tempo of each of our ships has gotten greater, and that stresses the ships even to a greater degree, gives us less time to do maintenance. All of these things lead to problems with respect to corrosion control and the availability of our fleet to perform its primary function.
Despite the latest research, salt water will remain one of the U.S. Navy's worst enemies for years to come. Unfortunately, the corrosive effect of salt doesn't stop at the shore. Thanks to the damage caused by rock salt on our roads, these robots are assured job security. Since 1946, nearly 1,000 ships have been mothballed at Suisun Bay. Corrosion and decomposition will return on Modern Marvels. Automotive corrosion. It costs America over $23 billion each year, or $115 for each driver on the road. The main cause? Rock salt. The 16 million tons of it applied to U.S. roadways each winter do much more than just melt snow. Melting fresh water with salt creates salt water and massive corrosion problems.
It's very effective from a de-icing perspective. The problem is it has damaging effects on automobiles and infrastructure.
Rock salt is the primary contributor to corrosion that we see in underbody areas and on the sides of the vehicle.
It breaks down the inner metal surface and causes rust at the prone areas, such as door seams, headlight bezels, trunk bezels, rocker panels, wheel wells.
Metallic road features like bridges also corrode faster due to rock salt used for de-icing. Rock salt isn't the only means of de-icing roads. Calcium magnesium acetate is a far less corrosive yet equally effective alternative. But it's 30 times more expensive, making rock salt the de-icer of choice. American automakers battle rock salt's corrosive effects at places like the General Motors Proving Ground in Milford, Michigan.
The GM Proving Ground goes back to 1924. It's about 4,000 acres. There's about 120 lane miles of test roads. About 4,000 people work at the facility, and a lot of different test labs and vehicle development, validation, and durability occurs at that site. And the testing process takes us anywhere from 12 months to 20 months to get a full, complete evaluation of a vehicle.
To assess resistance to corrosion, the research team subjects cars to serious abuse.
This is the grit trough facility. This is used to create underbody splash for our vehicles undergoing corrosion test. It applies a mixture of grit and different contaminants to the undercarriage of the vehicle and the engine compartment of the vehicle. There's a mixture of sand, crushed stone, cinders, various different elements, and basically we're getting the same contaminants on the vehicles on test as what we see in the real world.
Prior to the 1950s, corrosive rock salt wasn't a concern for car owners.
Vehicles produced in the 1920s to the 1930s were built on a much sturdier frame. Thicker metals were being used, thicker body panels were being used. Less road salt was being applied in the 30s itself. In the late 50s, the vehicles lightened up from heavy steel to light steel to improve performance of the vehicle. Those vehicles corroded out much faster. Most consumers in the 50s and 60s only kept a car 4 to 5 years and it was gone.
Kurt Ziebart, a German auto mechanic who immigrated to Detroit, Michigan in 1951, saw rust as an opportunity.
He was amazed at the amount of rust on vehicles throughout the United States. He wanted to find a solution to that, and that solution for him was rust proofing.
Ziebart applied a corrosion-resistant oil-based spray to the undercarriage and interior panels of cars, where trapped moisture causes rust. By the 1970s, Ziebart rust proofing had hundreds of franchises. Twilight Zone's Rod Serling is their spokesman, and a catchy slogan.
Ziebart, it's us or rust.
The 1970s also saw American car makers come under fire from the U.S. government. A federal economic report cited the U.S. auto industry as the largest corrosion problem by cost in America. Car makers responded by introducing galvanized steel in vehicle construction. In galvanizing, steel receives a thin coating of zinc, applied either by hot dip or electroplating technology. The zinc oxidizes and forms a barrier to protect the steel. But if the coating is damaged, the zinc also acts as a sacrificial anode. It corrodes and leaves the exposed steel rust-free. You'll also find galvanized pipes, corrugated sheet metals, nuts, bolts, and nails. But galvanizing alone wasn't enough to satisfy demands to control automotive corrosion.
In '79, the Canadian government mandated that a 3-year warranty be provided to Canadian consumers on corrosion for all vehicles made by General Motors, Ford, Chrysler, and American Motor Corporation. That, in turn, required the United States to provide the same warranty on a competitive nature to its consumers who were purchasing the same vehicles.
Things have only gotten better since then.
Today, a consumer will keep a car on average 9.3 years. Far outlast the automotive manufacturing warranties, which are 7 years, 100,000 miles currently.
American cars owe their extended lifetimes to deep corrosion research, like that done at GM's Salt Mist facility.
This facility is designed to expose the exterior of the vehicle to salt mist that's consistent with what a vehicle would get when it's exposed to coastal areas, and also what a vehicle would get as it's trailing another vehicle on a salt-covered road. A test vehicle is exposed to this facility and this test input numerous times during the corrosion test.
Vehicles will undergo 100 repeated cycles of each test over 20 weeks to approximate 10 years of corrosion.
The dedicated gravel road facility is designed to produce chipping damage to the lower body vehicle areas and the underbody vehicle areas. The facility itself is designed with a cover over it so that we can have consistent testing whether we're in rain or freezing conditions. The dedicated gravel road is 1,000 foot long, and we use the size and shape of stone that is optimized to create the most significant damage in terms of chipping on the vehicles.
After more splashing, jostling, and general mistreatment, the cars are ready to rust, and rust fast.
We bring that vehicle back to the building, and we put it in the corrosion chambers. These chambers are maintained at 120 degrees Fahrenheit and 100% relative humidity, which is a very corrosive and severe condition for the vehicles. These chambers are used to both accelerate the corrosion process in general and to also allow us to test both summer and winter and maintain a consistent corrosion rate for our test. Once we've baked the vehicle in these chambers, we have an ability to look at the vehicle and verify that the performance of all of those components and materials working together ultimately meet our customer requirements.
They verify that by literally ripping the car apart.
The teardown process involves completely disassembling the vehicle, removing all of the interior trim, the steering wheel, the seats, and completely getting the body ready so that we can disassemble the body spot weld by spot weld. This process will take a matter of several days to get the body ready so all the components are laid out on the table so that the various design engineers have an opportunity to come out, look at their components, pick them up, hold them in their hand, turn them around.
And as we find issues, we change the design, change the material, or change the process to correct that issue before it gets into the hands of the customer.
The challenge is to build cars that stand up to corrosion, but can also be made economically.
I can build a vehicle that's corrosion resistant and corrosion proof, but the average customer could never afford the vehicle. So you got to balance cost as well as performance and durability.
In a world of decay, nothing lasts forever. Not even plastics, which have a lifespan measured in centuries. And if you're wondering where plastics go to die, it's the middle of the Pacific Ocean. And that is a big problem. The relays on most airbag systems are gold-plated. Gold resists corrosion on this life-saving device. Corrosion and Decomposition will return on Modern Marvels. Plastic. It's everywhere. The world produces 110 million tons of it each year, and only 1% of that is recycled. What happens to the rest of our discarded plastic? Unlike metals, plastics don't corrode. They don't even rot. But they do break down when exposed to sunlight through a process known as photodegradation. Ultraviolet radiation in sunlight causes chemical compounds called polymers to cross-link. This makes the plastic brittle, allowing it to break down into smaller and smaller pieces.
You can think of it in terms of the vinyl top on a car or the vinyl dashboard in a car. If you don't put your armor all on it and resist the UV degradation, it becomes embrittled, it cross-links, and it cracks.
Captain Charles Moore understands plastic. For over a decade, he studied it as it collects in an area known as the North Pacific Gyre. That's where plastics go to die.
It's easily 10 million square miles in extent and the size of the continent of Africa. The North Pacific subtropical gyre is a circular current that's caused by a high-pressure system. It circulates in a clockwise direction and pushes down near the center and creates a lower sea level. So you get this kind of a toilet bowl effect of currents that pull debris from the Pacific Rim and bring it into the central part of the North Pacific. Anything that floats will make it into the North Pacific subtropical gyre, everything from refrigerators to toothbrushes. Predominantly, what we see out there is broken down bits of consumer plastics that are now outweighing and in some cases even outnumbering the natural food out there.
Plastics can take up to 5 years to journey from North America to the gyre, breaking down through photodegradation during their journey to create a plastic soup. Captain Moore and his crew aboard the research vessel Alguito trawl the gyre surface with a 1/3 millimeter mesh net to gather samples for their study.
Documented, this is the first one of the repeat survey. We would expect our trawls to be something in the order of 100 times as bad as they were in 1999. This appears to be what we're finding.
The problem is more than just a scenic blight on this remote area of ocean. Plastic is making its way into the food chain. Millions of seabirds, marine mammals, and fish die each year by ingesting or becoming ensnared in plastic refuse.
The chemicals that are transmitted up the food chain to fish that we consume is a concern. It's a concern for our own health.
Research suggests that toxins found in fish that consume plastics can be linked to cancer, liver damage, and reproductive problems in humans who eat tainted fish.
This stuff got a lifetime on the order of centuries, and no one alive today or their children's children will be in an ocean free from this pollution. We've got to stop putting it in.
Unlike plastics that slowly photodegrade, organic matter goes through a more rapid breakdown. It's called decomposition.
Decomposition is the process by which things like earthworms, bacteria, and fungi help to break down the recently dead organic matter from plants and animals, recycle that material so that the nutrients can be used again, and also in that process releasing carbon dioxide.
Plants grow when they take up carbon dioxide from the atmosphere and combine that with water to make glucose that feeds them. But once plants die, microorganisms begin to attack, releasing the nutrients stored within. New plants use those nutrients for growth. The carbon that was stored in the dead plants is released into the atmosphere to be used again. Decomposition may be essential in nature, but it has a high cost for civilization. 25% of the world's harvested produce is lost to spoilage. Additionally, microbial decomposition of food results in the release of toxins, which are harmful when consumed. Decomposition also hits us where we live. Buildings fall victim to wood rot, the attack of fungi on wooden timbers, resulting in $17 billion of structural damage annually. But ironically, in America's garbage dumps, one place where we'd expect to see decomposition occur, it's being impeded.
In a typical landfill, waste is brought in, it's covered, liquid is diverted from that landfill. So it's basically a dry tomb, like a mummy's tomb.
The layers of earth that cap conventional landfills create an airtight seal, dramatically slowing the decay of refuse trapped inside.
It's like the Dead Sea Scrolls. You can dig that stuff up later, and it's still there. So where the science has gone now is to bioreactor landfills.
Bioreactors convert solid waste into usable energy in the form of methane gas by introducing fluids that accelerate decomposition.
We're constantly controlling the flow of the liquid into the landfill. We're trying to achieve a 30% moisture content in the waste. We think at that 30%, that's when decomposition will start to be accelerated.
The most advanced bioreactor on the planet is outside Winter Haven, Florida.
This is like the epicenter of world bioreactor landfill research is right here in Polk County. This is a large landfill. This is 3,000 tons a day of garbage coming in the door. That's a lot of garbage. Is about 40% of that garbage is putrescible. It's either paper or food waste or yard waste. And so the little anaerobic bacteria, anaerobic means they don't have any oxygen in there, and they eat that stuff, and they produce lots of methane, biogas.
Capturing that gas is critical to a bioreactor's construction. Thick plastic sheeting lines the bottom of the bioreactor cell. Irrigation pipes set atop 20-foot layers of solid waste pile up over the base. A giant pyramid of waste builds with each tier added. Waste fluid known as leachate collects in the bottom of the pile and is pumped to holding tanks. The leachate is then pumped through the irrigation pipes into the waste, speeding decomposition. Wells sunk deep into the pile tap methane gas produced by bacteria feeding on the garbage. The bioreactor is covered with thick plastic sheeting that prevents methane gas from escaping and keeps unwanted rainwater out.
What you see on the side slopes here is a 16-inch HDPE pipe, and what it does is it takes the methane from the landfill gas extraction wells and channels it over to the waste-to-energy facility just north of the property.
Over 500 homes are powered by methane derived from this landfill. That may not seem like much, but the U.S. Department of Energy estimates that if all landfills were bioreactors, they could supply the electrical needs of over 3 million homes. But accelerated decomposition also has another benefit, reducing the size of the solid waste by 10 to 30%.
Our goal is to increase the decomposition to the extent that we can actually put more garbage in the cell while we're still using it, so we don't have to build as many landfills. I think the dry tomb concept is going away, and most people realize that long-term, getting the waste wet and getting it to decompose is the way to go, and bioreactors are just going to become everyday common practice.
We may also be seeing more of these little guys that can effectively recycle many hard-to-digest materials. They're every homeowner's worst nightmare, but they just might help us save our planet. Every year, 11 million tons of plastic, 10% of the world's total output, enter our seas. Corrosion and decomposition will return on Modern Marvels. These may be the world's greatest decomposers. They cause hundreds of millions of dollars in damage to America's wooden structures every year. Such destructive power makes termites many a homeowner's worst nightmare. They're the primary target of a $7 billion pest control industry. But these creatures are not only pests. Far from it.
They do an alarming amount of damage to buildings every year. But there are 2,600 species of termite, at least on Earth, and only a few of them are known to be pests. Termites play a very important role in the turnover of high-energy dead material and distributing that throughout a food chain or a food web.
Termites physically break down plant matter into smaller pieces, so that bacteria and fungi may chemically decompose the material.
I love termites. I've been interested in studying termites now for almost 20 years.
Dr. Jared Ledbetter's research focuses on the termite's ability to turn a seemingly indigestible substance like wood into a viable food. And his little friends may just be the key to world-changing advances in the field of energy.
Termites are not able to digest wood by themselves. There's a role of the microorganisms that live in the hindgut in the degradation of wood into some compounds which then can be used by the termite as a nutrient. In the gut of one termite, you may find as many as 200 or more species of bacteria and protozoa and organisms that you'll find nowhere else in nature. So we'll now take this slide of this termite gut microbial suspension and we'll get a very fundamental look at the microbes underneath the light microscope. And it is this amazing menagerie of wild-shaped organisms very dynamically swimming around and cavorting and turning and tossing. And so visually, very striking place. And I like to say that working on termite gut microbes is like working in a miniature Alice in Wonderland. It's almost psychedelic.
These microbes may make cellulosic ethanol possible. That's the biofuel game changer.
Science has a very good understanding of taking a simple sugar, like table sugar, and turning that into ethanol using yeasts. We know how to do that. But we have a very poor command of how we might change wood into anything. Is there any way to come up with a process to convert grass clippings or rice hulls or wood chips into a transportation fuel like ethanol?
Isolating the microbes that break down wood is step one.
By understanding that, that should give us some foundation on how we might engineer new systems, not having termites in the laboratory, but actually new systems, ultimately maybe in large fermenters like you'd have at Miller Brewing or Budweiser Brewing, to do this on a massive scale under very, very different operating conditions.
Coarse cellulose could supply up to 100 billion gallons of fuel each year, replacing over 2 billion barrels of imported oil, while slashing greenhouse gas emissions. But the termite harbors more treasures. Its microbial community may also offer efficient new ways of producing hydrogen gas.
Some of the microbes are able to convert cellulose and other components of wood into hydrogen, do so at very high rates, and are able to allow hydrogen to accumulate to very high concentrations.
One termite can convert a single piece of paper into 2 liters of hydrogen gas, making termites one of the most efficient bioreactors on the planet.
There are many different angles to studying the termite gut microbiology, many different things that it can tell us, each in their own right very interesting.
For now, the termite gut provides a safe haven for that microbial menagerie. Thanks to this lowly insect, we just might be able